So let's talk about expenditure minimization. Why do we need it? To answer this question, let's first ask another question. What happens to the maximization problem when price of one good changes? For example, let's look at this graph here. Initially, we have a utility maximizing point at A, where the indifferent curve U0 tangents a budget line, right? And now imagine we have the price of one good, let's say X1, decrease from B10 to B11, while the price of the other good P2 remains unchanged. As a consequence, the maximizing point will move to C, where the new budget line tangents another indifferent curve with a higher utility level, intuitively because a price decreases means something better for us, right, as consumer. So, however, we talked about it last week. When one price changes but the other doesn't change, two things happen to the budget line. The first thing is its slope is decreasing or less negative, meaning it's become flatter, right? So it moves outward, not parallelly, but shift anyhow outward. And this movement is called substitution effect. So if you move along the same indifferent curve as before, meaning the individual is kept on the same utility level, that means the movement from A to B. And it only deals with adjusting your consumption basket, the ratio of the consumption between X1 and X2 without changing your utility level. So there's a substitution effect. The second movement would be from B to C, the income effect. Because as price decrease, now individual can buy more. So this extra purchasing power will move him from B to C, from here, which is on a higher level of utility. And this is called the income effect because it has something to do with the real income, the real purchasing power. So now we can study this substitution effect using a dual problem of utility maximization, which is expenditure minimization. So why is it called dual problem? Because it comes from mathematical principles called duality. So for any constraint maximization, for example, here we're talking about utility maximization, we can always turn the focus to the constraint itself and set up the minimization problem, and in which we try to minimize our limited resource or expenditure or money needed to achieve a certain level of utility, which is now fixed at one point. So let's say we fix at the level U2 bar. The bar above the U indicates that it's fixed as a constant. Now, that's why we need expenditure minimization. However, not only that we could study the substitution effect, after we derive the minimal expenditure. We could also calculate something called compensating variation, which is the amount of money that we would have to pay an individual to keep him on the same level of utility as before when price change. So these are the things that we will learn this week. Okay, let's go. Here is some more illustration about income and substitution effect. This is the graph that we have seen on the last slide. And we also know that from the utility maximization problem, ultimately will we be able to derive the demand functions called the Marshallian demand function of each good, right? However, like it's showed here, this Marshallian demand function only show you the movement of A directly to C without saying anything about the movement from A to B, which is the substitution effect. We said that. So this demand function is called the normal demand function, where you keep income constant and you vary utility level. Yeah. Now, like what we just said in previous slide, we can use the expenditure minimization to estimate the movement from A to B. Here is how it works. So from expenditure minimization, we will also arrive at a demand function for each good, a different demand function. So this demand function is now called the Hicksian or the compensated demand function. Why compensated? Because the idea is we try to keep the person on the same level of utility, or the same indifferent curve. Here, U0, right? When A moves to B, there's a shift in the maximizing point from A to B. Then on this compensated demand, it moves from X1A to X1B, right? That's what we're interested in. And so compensated because we don't let the individual move from B to C. To do that, we have to pay him, or we have to take some income of him, right? So in that sense, the income effect is already compensated because there's no movement from B to C, which represent the income effect. Now, so again, that's why we're interested in expenditure minimization. Okay, so now let's do an example for expenditure minimization with subject to a constraint given by the Stone-Jury utility function before, but now we fixed it at a utility level constant. So let's do it and see how it's similar or how different from the case that we have with utility maximization before. But before that, note here that we, for easier computation or less messy, we just write B2 equals 1 minus B1 over here. That is B1 plus B2 equals 1, like before. So that's easier. So now let's write down the Lagrange function. So that is the graph functions of the original variables and the lambda, just like before. Now the objective function we have is the expenditure, so rewrite that. Okay, plus lambda times the constraint. So let's say in this case is x1 minus c1 to the power b1 times x2 minus c2 to the power of b2 minus the constant, right? Let's mark it separately over here so that we don't mess it up somewhere. Okay. Now, first order condition. Standard, very standard approach. Again, calm down. Take it slowly. We can do it. So we have the first one is the derivative of L with respect to x1, right? Which is now P1. X1 here, there's no x1 here. Good, don't have to care. And then plus lambda, right? And the one inside is now the derivative of it we have taken last week when we taken the derivative of the utility functions. Now we can just rewrite it again here, right? The second term is only constant. Keep constant now, don't have to worry about that. So b1 times x1 minus c1, right? To the power of b1 minus 1. Rewrite x2 minus c2 to the power of b2 again. And then, because u bar is a constant, is gone, equals 0. This is the first equations. Do the same thing for x2, which is now b2, right? Plus lambda times b2 again, right? And the whole term with x1 remains constant, so it's b1. Oh, sorry. So that is x2 minus c2 to the power of p2 minus 1. I make a mistake here, which is not so nice. So let's write it here. 0, 1, b2 now, here b2 minus 1 equals 0 also. This is the second equation. And the last one is with respect to lambda, right? The whole constraint again. So nothing really new over here. So you have x1 minus c1 to the power of b1 times x2 minus c2 to the power of b2 minus the u bar, the constant utility level, is now 0. This is the third. What did we do before with utility maximization? We rearrange the first two equations and then we divide one by the other, right? Do the same here. So let's rearrange it in a way that brights go in one side of the equations and the rest goes in the other side. So in this case, let's write it here. 1 divided by 2 would be P1 over B2, right? You actually, if you put B1 and B2 to the right hand side of the equations, then you have a minus over here. But because you have minus both above and below, at the end it cancel out. So we don't have to write it down here. So just forget it. And then what is left in this part? Lambdas cancel out, right? Don't have to rewrite it again. So you have B1 over B2, the two constants, the two exponents. And now let's simplify directly this one. F1 minus C1. On the numerator you have B1 minus 1 to the power. And then the denominator you have B1. So at the end what do you have? You have still the power minus 1 over here, right? And the power minus 1, which is also can be written as 1 over x1 minus c1, right? And then it comes to x2 minus c2 to the power of b2, but then divided with the same thing, but to the power of b2 minus 1. How much do you have with the exponent? 1, right? So 1, which means it can stay on the numerator. x2 minus c2, right? And here, look at this. We had something like that before when we derived the utility, right? The utility maximization problem. We had something like that before. And here you could say that actually the same thing happens because on the right hand side you had the ratio of the two marginal utility, and still on the left hand side the ratio of the two rises. So there must be something similar underlying this first order condition, which is the marginal rate of substitution again must be equal the ratio at which the two goods traded on the market, which is the ratio of the rises. Now, just so you remember. And then here we could solve for either x1 minus c1 or x2 minus c2, and we go further from there. Up to you, but here I will solve for x2 minus c2. How? Multiply both sides by, because we want x2 minus c2, so everything else we have to cancel out. So you have to multiply by its revert. So let's say x1 minus c1, then times b2 over b1. So that's the revert of this part over here. Yeah. That means we have b1 over b2 times this term, this guy over here. So, but I write the parameters first now. b2 over b1 and times x1 minus c1 equals the whole thing's here in the pink box gone. So that means you have x2 minus c2 all alone on the other side. Last columns 4. I know that I'm repeating myself too often, but again, this is very similar to what we had with utility maximization. And what can we do now with this fourth equation? We plug it into the third equation. Where? right? And then we solved for either x1 or x2. Okay, let's continue. Now we plug, or we substitute 4 into 3, right? That means 3 would be equivalent to x1 minus c1 to the power b1, no? And then times x2 minus c2 to the power of b2. But x2 minus c2 is this whole term. So let's plug it in. Now, p1 over p2 times b2 over b1. And then times x1 minus c1. Everything to the power of b2. And you can already put the u bar to the other side, right? Now let's simplify it. Let's factor out x1 minus c1 out there. So we would have x1 minus c1 here to the power of b1 plus b2, right? These two terms times together. That means you sum up the exponent. So b1 plus b2. And then the whole term inside except this again to the power of b2. But remember, in the beginning we have b2 equals 1 minus b1, right? We said that in the beginning. So here let's substitute it back. I mean, you can leave it like that and remember this, but let's arrive to something like more comparable to what's written on the slide. Yeah? So you would have b1 over b2 times 1 minus b1 over b1 to the power of 1 minus b1 equals u. And then we want to solve for the 1x, right? And here the remaining is x1. And because b1 plus b2 is 1, right? So this you could write it is x1 minus c1 to the power of 1. Don't have to write it again. U. And then put the whole term of this in the square bracket on the right hand side. How? By multiplying both sides by its reverse, right? So its reverse in this case is, I would change again, oh, this is the square bracket. So its reverse will be b1 over b2, hold on, 1 minus b1 over b1, and then to the power of what? The reverse. This is b1. b1 minus 1, right? And now you can also put c1 to the other side. to arrive as H1, and let's denote it H here, YH. We will write it later. Sorry, the U bar. So U should be U bar times, now you could think about it, now let's put like everything with the same index, P1 over B1 to the power of B1 minus 1, right? And then on the other thing you would have 1 minus B1 over B2 to the power of also B1 minus 1. Now this is a little bit deviated from the result on the slide. However, it's actually exactly the same thing. If you manipulate the exponential the algebras a bit, it will be the same thing. And then we could plug this H1H into where? 4, right? And then put C2 to the other side to solve for X2. Here I will not do that, but we have into 4 to solve for X1H, which is X2X. So X2H would be U bar times, I missed something here, C1, okay, B1 to the power of B1 times to the power 1 minus B1 minus B1 plus C2. And this function, why is called H? Because it's called Hicks demand function, or compensated, because the income effect already compensated and only the substitution effects left in this demand function. And it shows you if the person were kept on the same utility level, like the U bar, the constant, how the how the quantity demanded will change when price changes, right? And there's like a constant C1 and C2 over here, which doesn't get associated with any prices or parameters, say that has to be consumed anyhow, right? And irrespective of your utility or prices.